So with that, let me introduce the speaker for this evening, and that is Dr. Keith Swenson, sorry. And he's trained in geology, zoology, medicine, a whole bunch of different fields. And he's focused on geology for quite a few years. He used to be president of the Design Science Association in Portland, a similar organization to what we have here up in the northern Seattle area. And he's led a lot of tours, geology tours, Mount St. Helens, maybe Yellowstone as well, and Grand Canyon as well. So he knows a lot about geology. If you go to the Grand Tetons, to the park there, you'll see signs which say these things all happened millions of years ago. Well, what is the biblical interpretation that we give to the Grand Tetons? So Dr. Swenson will answer that question for us tonight. So let's welcome him up here. Thank you.
Thank you. Well, thank you, Heinz. I want to introduce my wife, Connie, who's sitting down front here. We had a nice trip up here today. We left early thinking there might be traffic in the Seattle area, but it was rather moderate, so we sailed through nicely. That was fun. How many of you have been to Grand Teton National Park? Great, and if you haven't been, I'm sure you've seen the photographs someplace because they're used in advertising and everywhere. It's a very familiar. So I suspect most of you believe, probably based on personal experience, that the evolution worldview is heavily promoted in our national parks. Well, I agree that's true, but only partially so. Certainly the ranger naturalists speak of deep time and of evolutionary processes, and so do the park interpretive signs. But what does not promote such a view is the scenery. The rocks and fossils, the mountains and canyons, the plants and animals cry out for creation. And so today I would like to show you one example of that as seen in the remarkable geology of the Grand Teton National Park in Wyoming. And our program is titled, What Mean These Stones? Interpreting the Geology of Grand Teton National Park. Now, Grand Teton National Park was established in 1929, and it's located just 8 miles south of Yellowstone National Park. It occupies 310,000 acres, which on this map looks pretty small compared to Yellowstone's 2.2 million acres. That's a huge place. But together these two parks form the heart of a much larger region, which is called the Greater Yellowstone Ecosystem. And depending on how you define it, that includes over 20 million acres. Much of the land is in the surrounding national forests. There's the Gallatin to the north, and the Shoshone to the east, and the Bridger Teton to the south, and the Caribou Targhee to the west. And what characterizes this Greater Yellowstone ecosystem, I think, is wildness. Within the boundaries of that area are found healthy populations of essentially all the native species that were present prior to European settlement. That's like the grizzly bear and the gray wolf, the wolverine, the Canada lynx. To any visitor to the Teton Range, it presents a most striking landscape. It runs 40 miles in a north-south orientation. Its eastern front, seen here, rises dramatically from the floor of a valley that we know as Jackson Hole. There are no foothills to the Tetons. Jackson Lake, pictured here, is in Jackson Hole. Now, the rugged peaks of the Teton Range are just jagged spires. They have an aura of newness about them. The highest is Grand Teton, which is 13,770 feet, and 5 of the Tetons are over 12,000 feet. Now, some come to these peaks to ascend them. It's a rock climber's paradise. The rocks are highly resistant and strong and a great place to climb. But many more come to see the scenery. The Tetons are spectacular. This photo was taken from an old gravel road named Mormon Row, along which are preserved several old farm buildings from pioneer days. having trouble here. There we go. Now, but our big topic today is this. It's geology. We will explore the question of when and by what means this magnificent Teton Range and its companion valley, Jackson Hole, came into being. By the way, I think this is a nice slide, don't you think? Only the geologists understood that, right? Okay, okay. You'll get the meaning of that word in a bit. Let's begin with the big picture of the Earth itself. Geologists believe the Earth is composed of 4 large layers. From the center out, we have the inner core, which is made of solid iron and nickel, and then the outer core, which is also composed of iron and nickel, but in a liquid state, and it produces Earth's magnetic field. There's the mantle next, which is the largest portion of the Earth, made of so-called silicate rock. And then the crust. That's the thinnest layer. It's sort of like the skin on an apple. And it's broken into pieces that we call plates. And the crust is the substrate on which life exists, of course. And it's also the stuff out of which mountains are made, like the Tetons. And this diagram shows that there are two types of crust. On the right, you can see oceanic crust, and on the left, continental crust. And it's this continental crust that interests us most in discussing Teton geology. The continental crust averages about 25 miles in thickness. It varies quite a bit, but that's about the average. And it's composed mostly of igneous and metamorphic rocks. Rocks that have a similar composition to granite that we're all familiar with. And these granitic rocks have a lower density. They're lighter than the basalt, which makes up the ocean floor. So therefore, the continental crust, being somewhat lighter, tends to float higher on the mantle, and thus it forms the continents, while the denser basaltic crust sinks and forms the ocean basins. Now, here we see the same thing, the outermost part of the crust depicted, and at the bottom it says basement rock. And that's this granitic rock that we've just been talking about. And it forms over 95% of the crust of the Earth. And it extends way, way down, in actuality, 25 miles. So it goes much below what this slide depicts. In addition, notice that on the top of the basement rock, it's a pretty flat surface. And then piled on top of this surface are sedimentary layers of sandstone and limestone and shale, and they contain fossils. Now, probably the best place on Earth to view the crust of the Earth is here in the Grand Canyon of Arizona. And an understanding of Grand Canyon geology is extremely helpful in making sense of the geology of the Teton Range. Grand Canyon is a huge slice into the Earth's crust. It is 277 miles long, up to 18 miles wide, and averages about a mile deep. So in this photo, you can see there's an inner gorge. It's labeled in the foreground there, and it's a smaller canyon within the big Grand Canyon. And it's here that the Colorado River runs. And the walls of this inner gorge are made of that upper part of the crust called basement rock. And above it, or sitting on top of it, is a line, which I've drawn in white, and it's a dividing line that's called the Great Unconformity. You'll learn more about that in a minute. And so piled on top of this basement rock and the Great Unconformity are layer after layer after layer of sedimentary rock. They all have names, and the lowest one is labeled here, and it's called the Teton Sandstone. So here we are on a raft on the Colorado River within the inner gorge, that area I just showed you. And on both sides of us are the basement rock. And on the top, in the foreground there, up by the sky, you can see the first of the sedimentary layers, and that is the Teton Sandstone. This shows a close-up of that basement rock, what it's like. And it has two components, really. It has the dark stuff, which is a rock called Vishnu schist. Everything in Grand Canyon is named for deities, non-Christian deities, I guess we'll say. So this is the Vishnu schist. And then you can see there's a rock that appears to have filled cracks that once formed in this schist. And that rock is granite, but called Zoroaster granite in that location. So now let's look at that dividing line, that Great Unconformity. And here we see at the bottom the Colorado River. And then rising above the river is the uppermost part of the basement rock. Remember, it goes way, way, way below this. And then sitting on top of it is the Teton sandstone, the lowest of the sedimentary layers. And between them is the dividing line called the Great Unconformity. And you can see it better in this photograph, a close-up. And I put the evolutionary dates on this. You notice that the basement rock is dated at 1.7 billion years. And the Teton sandstone at 500 million years, a half a billion years. So in other words, the Great Unconformity, that dividing line, represents a billion years of missing time. Unusual. But this, the usual explanation given for this is something like this, that an ancient mountainous landscape once existed here, and over that billion years of time, it was gradually eroded into a relatively flat plain, as we now see. Well, here is Tom Vail. He's a Grand Canyon river guide, and in this photograph, Tom's feet are resting on the basement rock. He is pointing at the Great Unconformity, and above his arm is the Teton sandstone. And I think it's extremely remarkable and significant that this Great Unconformity, this dividing line, is not just found in Grand Canyon, but in numerous locations planet-wide. It appears it must have some sort of global cause. Now let's consider the Teton sandstone now in this photograph on both sides of the river. And as we view the Teton sandstone, a question arises. Just how big is this Teton sandstone? Is it confined to Grand Canyon, or does it extend further? And here's your answer. The Teton sandstone is not just a local Grand Canyon feature, but it occurs over much of North America. It is seen in maritime provinces of Canada, over eastern United States, western United States, and then goes way up into the high Arctic, to the top of the north part of Greenland there. Now, it's not called Teton sandstone in all these locations because different geologists discovered it at different times in different places and gave their own names to it. So when we go to Wyoming, which we'll be doing, there it is called the Flathead sandstone, but it's the same thing as the Teton sandstone. It's continuous with it. Now, on top of the Teton sandstone are other sedimentary layers piled up one after another, and they all have names. And you can see here the Bright Angel Shale, the Muav limestone, the Redwall limestone, and if you go to the very top, you have the Kaibab limestone, and I omitted some of them. And like the Teton sandstone, they all extend rather great distances. And the thickness, again, of this package of sedimentary layers is about a mile. Well, as we look at these layers, another question can arise, and that is, was there ever anything more on top of these layers? Is this the highest of these layers, a stack of sedimentary rocks was, or was it once much higher? And I'll give you the answer here in a quote from a book. This is a secular book from Dr. Stanley Buse. He edited it. And try to get the picture of what he paints as I read through this. He says, if you stand on either the north or south rim of the Grand Canyon, the soles of your shoes will rest on the cracked and weathered limestone of the Kaibab Formation. That's the top layer. As you peer into the deep chasm below, you will see a mile-thick section of strata that accumulated during the Proterozoic, Eon, and Paleozoic era. That's millions of years ago. Now turn your gaze skyward. Look up and imagine a section of rocks extending above your feet for approximately another mile, about the same distance above the rim as the bottom of the canyon is below the rim. This exercise will give you an idea of the great thickness of marine and terrestrial rock layers that were once deposited on top of the Kaibab Formation. These sediments once covered the entire southwest portion of the Colorado Plateau, an area that includes Grand Canyon. In case that wasn't real clear, let me say the same thing by using a diagram. And in this diagram, which is a cross-section of the geology of the Grand Canyon area, you see to the right an arrow, a red arrow, which is right over Grand Canyon, and it points at the top layer, the Kaibab limestone. And you can track that to the left as you mentally just track it to the left and follow it, and you see as you go north from the canyon and get up into Utah, layer upon layer of additional strata gets added on top of it until you get to the far side of the diagram. There's my arrow again pointing at the Kaibab, and below that arrow is all the Grand Canyon strata, about a mile or so, but looking out above it, there's a mile and a half to more than a mile and a half of strata above it. So was all that above Grand Canyon at one time? And the answer is it certainly was. We know that in part because there are remnants of it on the other side of the canyon. So that is a remarkable thing. We'll keep all this Grand Canyon stuff in mind, and we'll go back here to these mountains, the Tetons in Grand Teton National Park. And so how does it all relate? You can see in this photograph in the center, that pointy one is the Grand Teton, which is the highest of them. And this whole central group is called the Cathedral Group. I think you can probably appreciate how that name came to be. Let's look at one of the Tetons. And this is a mountain called Mount Moran. And we'll try to use this to see the connection between Grand Canyon and the Teton Range. Mount Moran, first of all, was named in honor of Thomas Moran. He was an artist, a landscape artist, very famous, who helped convince public and Congress to establish Yellowstone as the world's first national park in 1872. His artwork was so beautiful that it really helped in that movement. This Mount Moran here is over 12,000 feet in elevation. It's quite massive, and it has some interesting features. Here's a little closer look at Mount Moran. And Mount Moran is made of basement rock. It's largely gneiss, but it has schist, and there are veins of granite throughout this that are hard to see from this image. But this is the same stuff of Grand Canyon, in other words, the bottom of Grand Canyon, but at a much higher elevation. There's an interesting feature called the Black Dike. There's that vertical thing that you can see there. And that is, at some point in the past, a crack occurred there, and it filled with molten rock, and it solidified to this black dike, as it's called. And that extends about 7 miles to the west of here, so it's a big, big area. Now, you have a glacier, a small glacier called Falling Ice Glacier. When you look at the top of the mountain, most of the Tetons are rather pointy, but this one isn't. It looks like it's been eroded off, and indeed it has. And it's kind of a flattish surface, and that appears to be the top of the basement rock here. It's like the Great Unconformity would be in Grand Canyon. And then very interesting, you look at the very top of Mount Moran, there's a 50-foot layer of sandstone up there. And that is a remnant of the Flathead sandstone, which I told you is the same thing as the Teton sandstone. So was that entire sandstone layer once up there? Yes. Were other hundreds to thousands of feet of other strata once up there? Yes, it appears they were. And they've now been eroded off for some reason and by some mechanism. So all of this looks like what we saw at Grand Canyon, but it appears almost like the walls of Grand Canyon have been pushed up thousands of feet into the sky to form the Teton Range, and that basically is the case. Some mighty force has uplifted a portion of the Earth's crust to form Mount Moran and the rest of the Tetons. This is a critical diagram, and it explains a lot of what we're talking about. So it has to do with the Teton Fault, which is really the cause of the Teton Range and Jackson Hole. And you can see the fault line sloping there towards the left side, and it's labeled with an arrow pointing towards it. And the fault block to the left, which would be to the west, forming the Teton Range, is uplifted. And you can see the Teton Front labeled there, and I actually put the little sedimentary rock, the sandstone on top of Moran up there as green. And then the block to the right, forming Jackson Hole, it's been downdropped. And you can see the top of the basement rock is way down in the bottom of Jackson Hole, and Jackson Hole really is a big hole. How much displacement has there been along this fault? How much did these blocks move? And the answer is over 30,000 feet, 6 miles. And so you can picture the displacement along this fault as though you're flying in an aircraft at 30,000 feet looking down at the ground. That's the distance of movement along this Teton Fault. That's a lot. And you can see that Jackson Hole has been filled in First of all, some of the sedimentary layers that were once over the mountains are down in the bottom of Jackson Hole. They got dropped down there like the flathead sandstone. But also all kinds of other rocks have washed in there, and at the top there's a lot of glacial material that fills up part of Jackson Hole called glacial outwash. Here's another way of looking at the Tetons, an aerial view. And there you can see the Teton front, and I drew the Teton fault in white in front, in approximately its position in front of the mountains. And you can see that that whole front is uplifted. That whole block of earth there, 40 miles long, was uplifted, and it forms those very sheer cliffs, those really steep mountains to this east side. And as you look to the other side, it kind of gradually slopes off into the Teton Basin, which is in Idaho. The block has also been dissected by erosion. You can see it's now not just a solid block of rock, it's mountains and valleys throughout. And of course you see Jackson Hole in the foreground, and that's Jackson Lake, the largest of the lakes there. Here's a panorama of the Tetons. Shows you that the greatest uplift of the Tetons has been at the center. And there's Grand Teton. Mount Moran is shown towards the north. It's interesting that if you look at the center part of the Tetons, where the Grand Teton is, you don't find any of these sedimentary rocks. You find a little bit on top of Mount Moran, as I showed you. But if you go further north in the Tetons, you're going to find a lot of these sedimentary rock layers are still sitting on top of the Tetons. And if you go to the south, as we will do in a bit, you'll see the sedimentary rocks are still sitting towards the south. And if you go over to the backside towards Idaho, you'll find the sedimentary layers, many of them are still there. And in the foreground in Jackson Hole, of course, they were downdropped about 6 miles or so. So just trying to construct the tell you about the structure of this place, of how it's built. Another important diagram is this. Here I'm trying to compare the Grand Canyon with the Teton Range. And so on the left is Grand Canyon. So you might be in your raft going down the Colorado River at 2,500 feet, and you're right alongside the basement rock in parts of Grand Canyon. And on top of the basement rock would be the Great Unconformity. If you go to the Tetons, you find the basement rock is there, and on top of it is a Great Unconformity, an erosional surface, but it's pushed up to 13,000 feet. But it's the same continuous rock. The Teton sandstone is in Grand Canyon. It correlates with the flathead sandstone in the Tetons, just got a different name. The next layer in Grand Canyon is the Bright Angel Shale. Well, that's the same thing as the Grovant Formation in the Tetons. The Muav Limestone, well, that's the Gallatin Formation. The unnamed dolomite in Grand Canyon is the Bighorn Dolomite. And the Temple Butte in Grand Canyon is the Darby Formation. And the Redwall Limestone in Grand Canyon, a big cliff in Grand Canyon. Same thing as the Madison Limestone in the Tetons. It's all the same stuff. If you add up the thickness of the layers here, you get about 2,900 feet. But there's other layers that were on top of these also. So one estimate is that there was once 7,000 feet or so of rock, of sedimentary rocks, once piled on top of the basement rock. That is the basement rock that eventually formed the Tetons. So you got to figure, how did all that get eroded away? Well, another feature of the Tetons, here I'll just show you. This is a view from Rendezvous Mountain, where you can take a tram to the top. And it shows the sedimentary layers, which are tilting here. They're tilting because, of course, the mountains have been uplifted, and they are tilting towards the west. And I labeled the Madison Formation, which are limestone. You can see at the top the Darby Formation, the Bighorn Dolomite, and there's other layers. We'll come back to this in a bit. Another feature seen in the Tetons, and this is not a good slide of it, but it's all I could come up with, is that some of these sedimentary layers are bent or folded from their once flat position. And the remarkable thing is they're folded without breaking, without cracking. How could rock fold without breaking? Think about that one, and we'll revisit that also. Well, here I am. on the shore of Jackson Lake, holding two cobbles of a metamorphic rock called quartzite. Now, I don't know if you've heard of quartzite, but it's a real important one. Quartzite is known to have formed in the past when a lot of heat and pressure was applied to huge deposits of sandstone. This was during mountain building, probably. And the site of quartzite formation that's nearest to the Tetons is in central Idaho, about 150 miles away. And since quartzite in the Tetons is totally found as rounded pebbles and cobbles and boulders, that quartzite must have been transported to the Tetons by water. Here's rounded rocks again. These are quartzites mostly. They're all over Jackson Hole and the area. If you go just east of the Tetons, there are over 8,000 feet of strata that are mostly quartzite, 8,000 feet. Geologists have estimated that there's about 600 cubic miles of quartzite deposited in those areas, 600 cubic miles of quartzite rock. Quartzites are even found on the top of some of the Tetons. Here's creationist geologist Brent Carter at over 10,000 feet on the summit of Red Mountain in the northern Tetons, and you can see quartzites are abundant up there. So how in the world were all these river rocks removed from their place of origin in Idaho and transported to the Teton Range? Now, another feature of the Tetons is the presence of several small glaciers, about a dozen or so. And they formed during the Little Ice Age, a global cool period between about 1350 to 1850 AD. And as glaciers flow, they leave scratch marks or striations in the bedrock, and they leave behind piles of glacial debris called till. And when they go through a valley, they form it into a U-shape. Water forms valleys that are V-shaped, and when a glacier goes through, it looks like this. It's U-shaped, and there's a lot of them in the Teton Range. These rocks here, these huge boulders, are called glacial erratics. They are pieces of metamorphic rock, basement rock from the Tetons, that has been transported out towards Jackson Hole by ancient glaciers. And here is beautiful Jenny Lake, also a product of the glaciers. A mountain glacier once came down Cascade Canyon, which is in the middle of the Tetons there. It's a U-shaped valley, and a glacier flowed out of there onto Jackson Hole, and it carved a little basin, and it also surrounded that basin with a rim of rock known as a moraine, and when the ice melted, you had Jenny Lake. Well, you know, I've covered now many or most of the observable features of the Teton Range and Jackson Hole, and they're remarkable. Each of them is like a piece of a giant puzzle. And the question then becomes, how do you put the pieces together? That is, what does this geological puzzle mean? What is the true origin and history of the Teton Range and Jackson Hole? And as a starter, I think we must say that any theory of the Tetons must provide a satisfying explanation or interpretation for each of the following features we talked about: the formation of the basement rock, the intrusion of the basement rock by all that granite, the erosion of that great unconformity, the deposition of the sedimentary strata, the uplift of the Teton Range and the downdropping of Jackson Hole at the Teton Fault, and the erosion and transportation and deposition of thousands of feet of sedimentary layers and basement rock and quartzites, and also the glacial features must be explained. So how do you approach a problem like that, and how do you try to come up with some answers? A good place to start is to form a relative chronology, which simply means you try to put the events in order. Don't give ages to them right away. Just say what happened first, what second, and so forth. And I made an attempt to do that, and here's my attempt at a relative chronology. First of all, the basement rock, being at the bottom, likely was put down first. Make sense? Geology is hard, you know. Next, the cracks must have formed, and molten rock came in and formed those granite dikes. Next, some great erosive force had to shave off the top of them to form the great unconformity. Next, the first sandstone layer had to come in, followed by all the other sedimentary layers. Sometime after that, we had to have great uplift at a fault, the Teton Fault. So everything got uplifted. Then you had to have massive erosion, where you remove thousands of feet of the sedimentary strata, you erode into the basement rock itself, and of course move all those quartzites into the area. And lastly, glaciation occurred during an ice age and caused its distinctive features as well. Well, let's turn our attention now to where most people who are visitors to Grand Teton National Park, where they get their information, and that is the interpretive signs by the National Park Service. And a good place to start here is on Rendezvous Mountain, as again is towards the south end of the Teton Range. You ride a tram up, and at the top you meet a series of interpretive signs, and I want to just read a little bit of these for you. And this one says, and I'll skip a little bits of it here for sake of time, but the Teton Range was created. That's an interesting choice of words right off for an evolutionary sign. But the Teton Range was created as a result of two mountain building events, one that caused uplift of the region approximately 55 million years ago, and a second which occurred approximately 7 million years ago. The more recent event is responsible for the creation of the Teton Fault. The core of Rendezvous Mountain is comprised of an igneous rock dated to 2.7 billion years old. That's older than the Grand Canyon rocks. Overlying these ancient basement rocks are sedimentary layers, which were deposited in and adjacent to shallow marine seaways and were laid down from 510 to 354 million years ago, when the environment resembled a tropical setting. The gap in the geologic record, that is the great unconformity, the gap between the basement rock and the sedimentary rock is over 2 billion years in this location. And regarding the glaciers, it says they formed 130,000 to 160,000 years ago. So what is the message that the average visitor might take away from all of this? Not the details perhaps, but what's the big idea? And I think the big idea that one would take away is the Teton landscape formed over billions, hundreds of millions, and hundreds of thousands of years. And some layers were deposited by shallow tropical seas, a feature we find on Earth today. But let's move on. Mount Moran also has a sign, and the sign reads in part, the gneiss and granite, the rocks that make up the basement rock, the gneiss and granite are among the oldest rocks in North America, 2.7 and 2.5 billion years old respectively. The vertical black dike, which you saw, is said to be 775 million years old. Tan sandstone, that is the flathead sandstone I showed you, caps the summit of this massive peak, and that it is the remnant of a 510 million year old beach that stretched for hundreds of miles north and south of here, quite a beach. The message that I think you would take away from Mount Moran signs would be the rocks forming Mount Moran are millions and billions of years old. One very expansive sedimentary layer, the flathead sandstone, was simply an ancient beach, another geologic feature we experience today. This photograph shows a little bit of the track of the Teton Fault, visible, outlined in white, and it has its sign as well. And the sign reads, the Teton Fault began moving roughly 9 million years ago, generating earthquakes that shook the landscape. Each earthquake, up to magnitude 7.5, lifted the block, building the range one step at a time. Future earthquakes will continue to shape this landscape. So the earthquake occurs, the mountain moves up a little bit. Long time later, another earthquake moves up. So the mountain being built incrementally over a great period of time. The message is, for millions of years, the fault has been active, is still active today, and will continue into the future, forming the Teton landscape incrementally, step by step. In other words, the Tetons in Jackson Hole are not, it would be saying, not relics of a great catastrophic event of the past. They are simply due to the normal ongoing operation of nature. Last sign, young, restless, and still rising. As the mountains rise, wind, water, and ice wear down the jagged skyline and erode away sandstone and limestone layers. The landscape continues to change. The message here, processes we are familiar with today, like erosion by wind and water and ice, are responsible for the slow removal of the Teton's sedimentary layers. So the main themes I see relevant to our worldview, at least, here in these signs are naturalism, deep time, and something called uniformitarianism. Let's just define those. Naturalism is simply a philosophical belief that nature is all there is, was, or ever will be. That's basically a quote from Carl Sagan. Therefore, science must explain the origin of all things solely by means of natural processes. In other words, no supernatural creator or sustainer of the world is allowed, and of course, none was mentioned on the signs either. Deep time simply refers to the origin and history of the earth and the universe and life being understood in terms of unimaginably long periods of time, measured in millions and billions of years. Some dates are given there. This is an important word, an important concept, I think. Uniformitarianism, it's a belief of evolutionism that ancient geologic changes generally occurred slowly and gradually, much like we see today, without global cataclysm. The statement that you commonly hear associated with this is the present is the key to the past. If you understand the past, you just look at what's happening today in the present and extrapolate back into the past. Is that the case? Well, there are many examples given of uniformitarianism in the explanations on these signs, and let me just review those. Examples of uniformitarianism in the Tetons would be sedimentary layers being deposited slowly in shallow tropical seas, an expansive sandstone layer forming as a beach, thousands of feet of sedimentary strata gradually wearing away by the usual operation of wind, water, and ice, large rivers transporting hundreds of cubic miles of quartzite, the hardest rock in the Rocky Mountains, by the way, into the Teton area, and earthquakes of a magnitude seen today gradually forming the entire Teton Range. What might visitors learn that might be relevant to biblical worldview here? Well, I think from naturalism they could infer that God's really not needed. From deep time, certainly could infer that the Bible chronology is wrong. And from uniformitarianism, well, that's really a statement there was no Noahic flood. Everything has been slow and gradual in the past. Now, there's a whole lot more to the evolutionary view than what I've given you here. A lot of detail, a lot of complexity, and if you're interested in exploring it, there's a lot of resources you can look at. In fact, I have a reference list on the back table you can pick up if you like. There's one particular book that's good on this. It's by David Love, and ironically it's called The Creation of the Teton Landscape, but it's totally an evolutionary book. Well, that's one view. That's the evolutionary view. Let's go to a biblical view of the Tetons. Do we have any alternative here? So when we look to the Bible, I think right off the bat, we can replace naturalism with supernaturalism, because the Bible teaches that God created all things and that he continues to uphold his creation. Likewise, deep time is rejected, since Scripture informs us that Earth history is measured in thousands, not millions or billions of years. Also, the philosophy of uniformitarianism should be replaced by catastrophism, because the Bible indicates the past was dominated by a global earth restructuring flood. In a similar fashion, the standard evolutionary geological column can be replaced by a biblically based chart, like the one by Tasman Walker. Now, if you're not familiar with these charts, just forget about it. You don't have to know anything about it, but some of you are, I'm sure, familiar with these. Let's look specifically then at the Tetons and just go in order through the formation of the Tetons and make some comments here. Now, concerning the basement rock, that's the first thing we got to explain. And the majority view among biblical creationists is simply that the basement rock is creation rock. It's the bottom, it's when the earth was created. In Genesis 1, the earth was created, had to be created of rock. And so the basement rock logically is creation rock. Formed supernaturally during creation week, most creationists seem to place this on day one. Just to give you a quote from a geologist, Dr. Andrew Snelling, he summarizes his view this way: Hebrew scholars are comfortable that the biblical text allows the earth at creation to be differentiated into core, mantle, and crust, with a rocky surface covered in water. He says there's also good scientific reason for postulating that God differentiated the earth into core, mantle, and crust, much as it is today, right at the onset of creation. And then he goes on to give a detailed explanation of his scientific reasons, which we can't get into, but the reference is on your list if you're interested in pursuing that. Of course, another issue might be that there's this metamorphic rock. You know, metamorphic rock is one kind of rock gets put under heat and pressure, and it changes to another type of rock. And so that's called metamorphism. And a lot of that rock in the basement rock is metamorphic rock. And so the issue is, how did that come to be? And I guess you've got three options, and it's a debated issue, but it could have been created by God as metamorphic rock, I suppose. Metamorphism could possibly have occurred rapidly during creation week, or rapid metamorphism could have possibly occurred during the flood. And these are big questions to which I have no complete answer. I suppose the first thing you could say, if God created rock to look like it had been metamorphosed and it hadn't, was that deceptive on God's part? I'll leave that for you to think about. The second thing is, the secular view is that it takes extreme heat and pressure for millions of years, and that's mandatory for producing this large-scale so-called regional metamorphism that we see with the basement rock. So is it even thinkable that metamorphism could have occurred rapidly during catastrophic conditions like day 3 of the creation week or in the early flood? Lastly, you're familiar perhaps with Michael Ord, who has spoken up here in Seattle, and he has an idea about asteroid impacts having a major role in the flood and in forming some of the features of the earth, and could that have played some role in causing metamorphosis in this basement rock? Well, as I said, I have no final answers. It's a matter of discussion, and people are talking about this and working on it. But the most helpful resource I found was the one listed at the bottom, again on your reference sheet, again from Andrew Snelling. And he presents what I think is fairly compelling information that suggests that rapid metamorphism during extremely catastrophic conditions could have occurred during the formation of the continents, like on day 3 of creation, or during the early flood. Perhaps that is the case, something that one could dig deeper into. Let's move on. After the formation of the basement rock, it had to be intruded by all these granite dikes, these veins that are the pink things in this photograph. This is a photograph from Grand Canyon, but the same pattern exists in the Tetons, so it's the same there. A quote is given from Dr. Stephen Austin, a geologist who has studied particularly Grand Canyon. He says, molten material appears to have been injected into large vertical cracks during an upheaval of colossal scale. You can say the sequence of this in the Tetons must have been that metamorphosed basement rock was formed first, then cracks must have appeared in it for some reason and filled with molten granitic magma, molten rock, that went into these cracks and then solidified, forming granite. Again, when did it occur? I think the two options are during creation week, like day 3, or in the early flood, possibly. Again, can't give a definitive answer on that, but stay tuned. People are working on it. After that event, you have to have the basement rock shaved off, eroded off, flattened off. Remember I said in the evolution view, it took like 1 billion years of erosion, flattened off the surface of that rock, which was originally a mountain range, it is said. So here we have the Great Unconformity from Grand Canyon, and a quote from Dr. Austin again. Most creationist geologists regard the Great Unconformity as the feature formed during the tectonic and erosive catastrophe at the onset of the flood. In other words, the initial onslaught of the flood acted like a giant buzzsaw, shaving off the surface of the pre-flood landscape. That is the predominant view for that. Let's move now here, and I think we have, as we get a little more further along here and into the flood, we have, I think, more clear answers. The sedimentary strata, a stack of pancakes of limestone and sandstone and shale and so forth. How did they get there? And the answer that is given, I think, by pretty much all creationists is that the sedimentary strata were deposited by Noah's flood. And they were deposited in the early flood, what's called the inundatory stage of the flood. When the floodwaters were rising, the sediments were being deposited layer after layer after layer. And of course, they contain fossils. Secondly, it says that the layers in any given area are often thousands of feet thick. If you have in Grand Canyon, all the layers together are like a mile thick, 5,000 feet thick. Of course, that's compatible with a huge flood event when you have that type of layers. Nothing like that is forming on Earth today. C says, generally, the layers cover vast areas. The Teton sandstone, I showed you the map. These are continental or beyond many of these layers. Of course, that's perfectly compatible with a global flood event. These layers contain fossils, trillions of them. That would be expected in a big flood event because you would kill trillions of organisms, and they would be rapidly buried and preserved so they don't rot away and they're not scavenged. They would be buried, and then when the rock turns to sedimentary rock, the fossils are formed. That would go well, I think. Now, sometimes, an E, as I showed you one example, these sedimentary rocks are folded without cracking. How could that be? That seems contrary to common sense. Rocks should break. But in an evolutionary view, a layer would be put down and take a long time, perhaps, to turn to rock. And then before the uplift occurred that bent it, millions of years might pass. Of course, it should break. But think of a creation view. The sediments are put down in the floodwaters, and very rapidly the uplift occurs before there's any time for the sediments to lithify or form rock. They're soft sediments. Of course, they would bend smoothly without cracking. So I think that fits the flood model very well. The last one is very important. I want to elaborate just a little more on that. Lack of erosion between layers. Here's some layers, and I put some white lines in there, if you can see. But where one layer ends and another starts, it's usually at a relatively flat line. These all tilt, but I mean, they're still relatively flat surfaces. They're not wavy up and down. There's no hills and valleys and canyons along those lines. And what that suggests is that one layer was put down, and before it had time to erode away or develop canyons in it or erosion of any sort, another layer came, and then another layer, and another layer. Rapid succession of layers being put down would look like this. And amazingly, secular geologist David Love of the U.S. Geological Survey, who's probably the expert on the Tetons, or was, he's passed away, but he looked at this and he wrote in his book, he says, the regularity and parallelism of the layers in well-exposed sections suggests that these rocks were deposited in a single uninterrupted sequence. It's exactly what a creationist would say. However, although Dr. Love concurs with the observation, he simply can't accept what he sees, because his quote continues like this. However, the fossils and regional distribution of the rock units shows that this is not really the case. The incomplete nature of the stratigraphic record becomes apparent when the spans of time between each layer, each of the various formations are plotted on a numerical time scale. Almost 2/3 of the pages of the geologic story are missing. If that's not quite clear to you, let me look at it this way. Here's a diagram I put together, and on the left, and it says Alaska Basin, but that's in the Tetons, so don't get confused. On the left is a numerical time scale, and just shows the millions of years ago, from 500 down to whatever it is at the bottom there. And to the right of that, those blocks represent periods of evolutionary history. Cambrian, Ordovician, Silurian, Devonian, Mississippi. If you don't recognize, up higher would be the Jurassic. So those are just evolutionary periods of time. But then to the right, I plotted in the layers from the Tetons, and focus on the Bighorn dolomite. That was deposited, I can't read the numbers from here, but it's 440 million years ago, probably over a great length of time, it was deposited. And then it sat there, and nothing was put on top of it until the Darby Formation came, and that was 80 million years later. So you've got this missing time, and there's other time gaps in there as well. Could one layer, like the Bighorn dolomite, sit there for all that time and not be eroded away? Think about 80 million years. It is known by the present rates of erosion, by the rivers today, that the continents on Earth would be eroded into the sea totally in somewhere between 10 and 40 million years. I hear various calculations, but somewhere there. And so 80 million years means the continents of the Earth would erode at least twice into the oceans. How could the Bighorn dolomite sit there for 80 million years? So the question is, there's the Bighorn dolomite, and on top of it is the Darby Formation, and you can't see the contact real well because there's talus and so forth there, but it's there, and it's in that approximate location I drew. Is that Bighorn dolomite been sitting there 80 million years waiting for the Darby to come along? It seems, unbelievable. Okay, moving on. We have uplifting and downfaulting at the Teton Fault. Great example of vertical tectonics, which is a phenomenon found worldwide. Michael Ord is an expert on this, and he says the uplift of mountains and the sinking of basins is a fundamental observation of geology across the Earth. What produces these vertical uplifts and downdroppings? Love suggests that the hot spot in Yellowstone, where all the molten rock is beneath the surface of Yellowstone, has been causing the land to rise and stretch and crack, and that contributed to the formation of this fault. And that maybe have some merits, but I don't think it'll explain all the features around the Earth. Michael Ord wonders if cosmic impacts had something to do with this. And again, this is a question that's being explored, and I don't have the full understanding of it. But I think another issue here is what was the rate at which this occurred? The uniformitarian or evolutionary view is that there were smaller earthquakes incrementally over millions of years, that with each one the mountain rose a little bit. And that's what all the interpretive signs say. But a biblical chronology doesn't allow that much time. It seems reasonable to me and to many others to think that 30,000 six-mile displacement could have occurred in one grand motion, or most of it at least. And why not? That would make good sense. And if that's the case, then the Tetons are not just an example of the ongoing workings of nature, but rather a relic to a great past cataclysm, which would be the flood of Noah's day. That would be, I think, a reasonable way to look at it. The Bible even addresses this in Psalm 104. Where I won't read the whole thing, but it says, the mountains rose, the valleys sank down. That's a perfect description of vertical tectonics. The problem here is that different versions translate it differently. And some say the mountains rose, the valleys sank down. Some say, well, the water rose and ran over the mountains into the valleys. I have one person who has some knowledge of this area, Dr. Charles Taylor, who wrote on this, and he says analysis of the Hebrew as well as the Greek and other translations of Psalm 104:8 and the context confirm the key verse is referring to earth movements, tectonic activity of the close over soon after the flood when the mountains rose and the waters retreated. So he and a lot of other people take this to be a statement that the mountains rose and the valleys sank down. I don't know exactly how important or how significant these photos are, but I thought they were really interesting in comparison with what we're talking about. There was an earthquake in New Zealand in 2016, and you can see here, this was a 7.8 magnitude earthquake. That's about the size they say they were when they built, the ones that built the Tetons. And you can see the fault there. I drew a line there, and to the right of the fault is a lot of black stuff, and then beyond that is the ocean. The black stuff is an area that was uplifted by this earthquake fault, and so that's ocean bottom. Now pretend you're standing right on my arrow where it says fault and looking at that, dark stuff. Here's what you would see. There it is. The ocean bottom there got thrust upward, and you can see the cobbles there, and at the top, which was the ocean bottom, you can see all the seaweed, all the kelp there. I thought this had a similarity to the Tetons, and also, did this go up slowly, a little at a time? No, the article says it exploded through the sand. I thought it was similar enough, I called that the Teton Scarp, and of course to the right is Jackson Beach. Here's the same event on land, and you can see here a sudden earth movement, and you have a scarp, like the Teton front there. It would be similar to that. And to the right, it's lower, that's Jackson Hole, and to the left, it slopes off towards Idaho. Well, I just think these pictures sort of correspond and give us maybe a little visual image of what might have happened at the Tetons. But I don't want to put too much stock on these. They may not be directly connected, of course. We need to address this: massive erosion, transportation, deposition of sediments. Recall that with the uplift of the Tetons, thousands of feet of overlying sediments were removed. Also, the Teton block itself was deeply incised, forming mountains and valleys, and hundreds of cubic miles of quartzite, the hardest rock in the Rocky Mountains, was plucked up, transported to the Teton area. So an important question is, does the biblical model, the flood model, provide an adequate mechanism for all this erosion? And I think the answer is yes, it does. In fact, it gives us an ideal mechanism. And that mechanism is the recessional stage of the flood. We said the waters rose and deposited the sedimentary layers, but then after reaching a maximum, they started to recede from the earth. And that would be after day 150 of the flood. The flood lasted 371 days or so. It wasn't just a 40-day flood. And so at this time, the mountains were rising and the water was flowing off the land into the newly forming ocean basins. The recessional stage of the flood lasted 220 days, and those who have studied this would say that the first part of that was a sheet flow phase, in which you had rapid currents going at freeway speeds or greater, probably hundreds of miles wide, hundreds of feet deep, and they could have stripped off layer after layer after layer of sedimentary rock that had been deposited, because it probably wasn't rock, it was probably soft sediments at the time. So it wouldn't be hard for sheet flow to remove all this recently deposited material, or at least a good part of it. And then as the waters went down and the mountains came up more, the waters got more channelized and more narrow currents, and they started forming canyons and would cut V-shaped canyons. In terms of Grand Canyon, the sheet flow phase would have removed all the overlying layers that are now in Utah, but not over Grand Canyon, and the channelized phase might have carved Grand Canyon. That's one view on it anyways. Consider the quartzites. Remember, 600 cubic miles of quartzite, hardest rock in the Rocky Mountains. It was eroded from uplifting central Idaho mountains. In other words, it was the mountains. It was mountains were made of this. And then it was transported at least 150 miles to the Tetons. This is a block that represents that quartzite. It measures 50 miles by 20 miles, and it's about a half a mile deep. The volume of rock removed from Idaho and transported to the Tetons is greater than the volume of water that was in the Lake Missoula flood, if you're familiar with that event. That's a lot of material. And so here's a little quiz for you. Pick the best agent to accomplish this impossible task. Powerful rivers flowing for millions of years. That's the uniformitarian view, or the recessional stage of the flood, of Noah's flood. That would be a biblical view. Take your pick. I think it's fairly obvious what would work better. Lastly, glaciation. A biblical view is that there was one ice age. The evolution view is there were multiple ice ages over a greater period of time. Biblical view is there was one ice age caused by and immediately followed Noah's flood, lasted a few hundred years, maybe 700 years or so. It was due to warm oceans because of tectonic and volcanic activity during the flood that caused a lot of evaporation into an atmosphere that was cool because of all the volcanic activity putting stuff into the air that blocked out the sunlight. So that was a recipe for a few hundred-year snowstorm. Now, in the Tetons, The ice age there was not, the geological effects were not due to the big continental ice sheets that came down from the north. That ice sheet stopped in Montana, didn't reach that area in the Tetons. But what happened is a big ice cap, about 3,000 feet thick, built up, developed on the Yellowstone Plateau. And then it flowed off into Jackson Hole, among other places. In addition, mountain glaciers formed in the Tetons and flowed down valleys like the one I showed that formed Jenny Lake. So here's a map during the Ice Age showing the Yellowstone Plateau covered by a 3,000-foot thick ice cap. And then where the arrow is in the lower left, that's a lobe of that ice sheet flowing into Jackson Hole, and then the mountain glaciers flowing into that as well. And you could say that the Ice Age put on the finishing touches to the Teton landscape. It carved sharp mountain peaks. It formed U-shaped valleys. It transported rocky debris such as glacial erratics that I showed you, and it also deposited all that outwash material into Jackson Hole. And it created the beautiful lakes like Jenny Lake. And so that covers the sequence of events that must have happened at the Tetons. And we got two views, two very different views. I would suggest that a catastrophic view based on biblical truth, including the flood, lends itself as a very good explanation for what happened here, and fits remarkably well. And there's a lot more work to be done, and a lot more to be thought about and explored. But it seems like the Bible gives a basis for a good model for how the Tetons were formed. Well, geologist Howard Bigelow Baker in 1938, he correctly wrote, "The doctrine of uniformitarianism leads to poverty where riches are to be desired." And I'd like to expand his quote and say, "The doctrines of naturalism, deep time, and uniformitarianism lead to poverty where riches are to be desired. To find riches, look to God and His Word." And let me leave you with a view of the Tetons taken from the Snake River overlook by the great landscape photographer Ansel Adams back in 1942. So, thank you.
Thank you, Keith, for that presentation. You presented us with a lot of information.
A lot of it.
And I'm sure
I shortened it too.
You shortened it too, good. And I'm sure some people are going to have some questions about what he talked about. And I want to remind you how we support this ministry is we take a free will offering. So those of you that wish to participate in that, the men will come forward in a minute or so, and feel free to put in that. Or there's also donation boxes in the back table. If you feel you'd rather do that, that's fine too. So raise your hand if you have a question. I'll bring the microphone around.
I'm just curious, the Ice Age, what land masses did it cover? Because I think of Noah's Ark and the water's going down, and then people had to live on the earth. And I can't imagine people living in the middle of the Ice Age.
Well, the Ice Age would have formed ice sheets that would cover only part of the earth. In our area, they would cover the far north, like Canada would be pretty much covered. And in the northwest here, the ice sheets carved out something called Puget Sound that you've heard of. I think you live right by it here, right? So the Puget Sound was carved out. The ice was 3,000 feet thick or so here. And the ice went down to south of Olympia and then stopped. In other places, it went further down, like it went to southern Illinois, for example. It carved New York down to Manhattan. But the land south of that was not covered with ice. And along the oceans, it probably wasn't covered with ice. So those ice-free areas. The climate would likely be different, like cooler and wetter after or during the Ice Age. It's interesting that the book of Job mentions snow and ice a lot. That's one of the earliest books of the Bible. And there's many statements about snow and ice. So you would think, according to the view here of the biblical ice age, even though the Bible doesn't mention the ice age, maybe the book of Job mentioning snow and ice is a little clue that he lived during that time and the climate was an ice age climate, perhaps. The Lake Missoula flood was a post-Noahic flood ice age event. And so a lobe of the ice from Canada came down and blocked the Clark Fork River in North Idaho and dammed it up so that all the valleys of western Montana filled with 500 cubic miles of water up to 1,000 to, well, near the dam, 2,000 feet deep. The dam broke, and then all the water rushed out and covered Washington, eastern Washington, came through the Columbia Gorge, down the Willamette Valley, and then out to sea. And so that's an event that biblical creationists certainly hold to, and secular geologists as well, with certain differences, but both agree that event happened, yes. You do. Yes, they are around. There's quite a few of them. An erratic is a rock from the Rocky Mountains sitting here in the northwest where it doesn't belong, and it's usually not rounded, so it hasn't been tumbled by water. It floated in. How? It was in an iceberg. So the erratics came in icebergs here.
Other questions somebody may have that they want to ask?
I was wondering how they could say that an earthquake of magnitude 7.5 or whatever happened millions and millions of years ago.
I agree. I would wonder that too. There's a great desire in geology, a philosophy of uniformitarianism that I mentioned, to explain things in a way that's compatible with what we observe on Earth today. In other words, I think it's a way of escaping from the idea of a flood, a catastrophic flood. But so it's a common thing to hear of something that we experience today recurring repeatedly and forming something in the past. Just like the Lake Missoula flood, there are people who postulate there were up to like 90 Lake Missoula floods over a period of time. Again, that's kind of an idea of uniformitarianism. It's a philosophy that I think is used in interpreting evidence, and I don't think there's evidence that somehow tells you there really was 7.5 earthquakes way into the past. They also may look at the most recent movement on that fault, and there's been a little movement after the Ice Age, and that was rather small, so they may look at that and say, well, that's maybe a 7.5 earthquake. But that doesn't mean the rest of them were in the past, or that it wasn't one big event.
Question here?
Why do you think that the scientific world has not come together and agreed that the Tetons is the same as the one on the other side of the hill, so to speak? And why have they not standardized that for all structures?
Well, that's a good question. I don't know for sure. I can guesstimate a bit, I guess. But clearly, historically, the names were different because different people were working in different areas. That's perfectly understandable. I think the people who have tried to correlate these layers and see that they fit together are probably more the creation community geologists, because, of course, that obviously fits our worldview. I think there is recognition also among geologists, secular geologists, that much of this is true also, but I don't think it's widely publicized or widely known. I can't fully answer your question.
Okay.
Excuse me. Are there any points from the cataclysmic studies in some Mount St. Helens that support the creation of the Grand Tetons?
The Mount St. Helens studies, showed largely that here we had a cataclysmic event that we witnessed and studied and so forth, And it showed that certain geologic features, which are normally said to take a long time to occur, really happened rapidly at Mount St. Helens, like canyons formed in hours, layers were put down in hours, and so forth. All of that, I think, lends support to a catastrophic explanation for other geologic features like Grand Canyon and even at the Tetons. I don't know if we link it to the Tetons more directly than that. I'm not thinking of an exact anything beyond that, but it certainly gives you the idea of catastrophic events being very capable of producing the geology we see today.
Another question here?
Yeah, thanks. I was trying to fix in my mind, you mentioned a real interesting part I thought about the erosion rates. If I understood that right, it was about 40 million years would have eroded the continents into the seas. Is that right?
Well, there's different people who have calculated this, and I've seen one of them published 10 million years, and others have published, up 40, okay. 40-ish. So I would say there's a range here, and
they probably assume uniformitarianism. That is the same processes as today.
They would assume that at the same rates that rivers erode today, so they would assume a uniform. Yes, that's true. So at that,
if it's net, is it net of? I think what we understand to be pretty small formative forces like volcanism and stuff. Is it net of that, or does it assume static that if you didn't form any more continents through volcanic or any of that kind of activity?
I think it's
erode in that high.
The opposition to the idea that the continents erode that quickly, the opposing view would be that the land has been uplifting at the same time maintaining our continents, like volcanic activity, but uplift. The problem with that is if there's been uplift to keep track of or to keep up with all that erosion, then the entire fossil record should have eroded off, and it's still here. So that would be an argument for that not happening. We got one up front here, too.
Question here.
Yeah, Devil's Tower.
Yes.
Which is so unique.
Yes.
Because I guess from my understanding, the rock formation in itself is just totally unique for the whole area around there.
Right.
How do you think that happened? I'm sure it happened, through the Ice Age and everything, but how do you suppose that exact mineral ended up where it did?
Okay.
I've always been curious.
Devil's Tower in northeastern Wyoming is a fantastic place, and it's called a volcanic throat, or it was the insides of an old volcano, and that what we see today would have been underground. It's not the volcano; it's some of the underground portion of it, part of the maybe say like a magma chamber or that, and so that is what everyone indicates that it is. So you can think of Devil's Tower as we see it today, and picture it being totally buried by sedimentary layers way up, hundreds to thousands of feet above it. And so the reason we see it today is that all that overlying material was eroded away. Not just around Devil's Tower, but over the whole area, because these layers extend great distances. So you'd have erosion of probably hundreds to thousands, probably thousands of feet of strata over most of northeastern Wyoming and out into the Great Plains and so forth. That's like what the recession of the flood would do. The other thing is that indicates it's not millions of years old, that it's not millions of years ago, is that tower is still standing. Because the surrounding land, everything got eroded away, and in fact, it's not piled anywhere, it's out of sight, it's gone, it's dissipated. But the tower still stands, and that tower is made of these columns that gradually are breaking off and falling. And so if it had been millions of years ago, that tower shouldn't be standing at all, it should be a heap of rubble, and it's still there. So I think it's an interesting structure and really speaks for a flood model, I believe.
This is part observation, part question, but in 1992, we went with Dr. Don Chittick to the Cowlitz River, and I know this is a little bit off the Teton subject,
That's okay?
but he showed us an island about 350 feet long and 100 and some feet high and 60 to 80 feet wide in the center of the river that formed within a period of about 9 days. There's solid igneous rock inside of it, all types of rock, and it's the geologic table completely reversed. Have you seen or heard that? I forget what it's called, but
You're talking about Decollett's River,
yeah.
and as a result of Mount St. Helens.
And it happened right after the eruption.
I can certainly understand an island of volcanic debris forming quickly. I'm not sure about a reversing of the geologic column, what that would mean exactly.
I don't remember. I just remember him explaining it to us, going through all of these different layers and showing us the sandstone on the bottom all the way up to quartzite type material on top. It was
I'm puzzled. I don't know that I
incredible.
can clarify that really. Interesting comment.
Well, thank you. We're going to bring the question and answer to a close, but Keith will be available and back to answer any other questions you may have. Let's just thank Keith for the presentation and Q&A.
Oh, just to say, if anybody wants references, they're on the table right behind us here.
Yeah.
So help yourself.
Yeah, and it's on the back table to the my left there.
Yeah. Okay.
So if we bring up the last slide here, I want to remember you to remember, for those of you who signed the sign-up sheet, that was for the email sign-up. Don't think you were signing up for the dinner and briefing with that sign-up. You got to sign up online, register online for that. So just to wrap up, next slide if you could. Take time to visit the book tables back there. We have for the Apologetics Forum, we have a table there that has 50% off the list price of a lot of books. And there's one in particular that you may be interested in. It's called The Puzzle of Ancient Man. And that's a special book we make available for $5 each. And there are a whole bunch of pamphlets, a bunch of books. There's that Geology table there, Patrick and Vicki Nuri's table there. Take a look at that if you may have an interest in that. There's lots of flyers on the back table there. If you take one of those and you want to, if it's available to you at your church, feel free to post it on those flyers in the church foyer someplace. Of course, get permission to do that, but that will help us to publicize the next talks coming up, which of course is Mike Riddle. The other thing I forgot to mention was that we have a DVD back there on the Apologetics table. It's called Fallout, and it's put together by Creation Ministries International, and it explains the problem we have losing our youth because they're getting inundated with, I won't call it teaching, indoctrination of evolution and secularism. And that's what we're trying to guard against. That's what this DVD is about. This is an interview that some people have done with university students, some who were raised in the church and left after they went to a secular college, and others that grew up in the church and they stayed with their faith, and they gives you the reasons why. You might want to pick that up and listen to it. So it's only 25 minutes long, but if you pick it up, you have to promise to listen to it and pass it on to somebody else. The other thing, if you look at our website, you can see what speakers we have coming up over the next 4 or 5 months. Mike Rill, of course, is next, and this is what he's speaking on. Dinosaurs and what they have to do with the age of the Earth. How do they help determine the age of the Earth? So the flyers for all that are on the back table. Pick up one if you want. And all this information is on the website too, of course. Okay, so with that, we're going to bring it to a close and to give you time to take part in the refreshments and to peruse the tables. Father, we just come to you just again to thank you for this time. We thank you for Keith's presentation. We pray that we can learn much from that and share it with our colleagues and friends and families who may not believe that you are really the Creator, Lord. And this is information we can use for that purpose. Thank you for Keith's ministry, and thank you for the time that we had together here. In Jesus' name we pray. Amen.